rocket burns fuel at a rate of 5.0 kilograms per second, expelling exhaust gases at a speed of 4.0 kilometers per second relative to the rocket. We would like to find the thrust of the rocket engine. So part A is asking us to model the fuel burning as a steady ejection of small pellets, each with small mass change m. Suppose to take a short time change t to accelerate a pellet to the exhaust speed v exhaust. Find an expression for the magnitude of the force that one pellet exerts on the rocket during the short time while the pellet is being expelled. So one notable thing that is going to be helpful for us to solve this problem is just Newton's third law, which basically says that action and reaction are equal and opposite. So from Newton's third law, we can go ahead and say that the force of change m on the rocket is going to be equal and opposite to the force of the rocket on change m. So you can kind of see that in my diagram to the right, where those arrows are the same magnitude, but in opposite direction, with the top arrow being a force that acts on the rocket, and the bottom arrow being a force that acts on the pellet. So since the problem is asking us to find an expression for the magnitude of the force of one pellet on the rocket, we can kind of use some of those figures that they've given us to help us wrap our head around this and come up with a model. So it gives us originally that the rocket burns fuel at a rate of 5.0 kilograms per second, which the problem gives us that it wants us, when we're modeling, to represent that as change m over change t. But looking at those units is going to be helpful for modeling this. So those units would be kilograms per second, and the speed of the fuel can be modeled by v exhaust, units of which are going to be meters per second. So it's notable that the units for newtons is kilograms per meters per second squared. So that means that if you multiply that change m over change t by v exhaust, you're going to get those units, the kilograms over times meters divided by a second squared, which is equivalent to newtons. So the way that I modeled this was just doing that. But the way I set this up, what I solved for was the force of the rocket on the pellet, and the problem is asking for the force of the pellet on the rocket. So we know through Newton's third law that that's just going to have to be opposite. So I just added a negative. But the negative is honestly super arbitrary, depending on the direction you make your forces in this. But because the problem gave the speed as positive, which once again, that's kind of arbitrary. Basically, it's arbitrary. I just wanted to indicate that they're going to be opposite. So yeah, that's the answer for part A. Okay, part B is asking us to find the rocket thrust for the values given above. So I just wanted to point out that here, that this force we're solving for is a force acting on the rocket, not a force acting on the pellet. Because if it was the way that the Newton's third law works is it's two different bodies. So it's not like the equal and opposite force is acting on the same thing. It's the rocket acting on the pellet, and then the pellet acting on the rocket separate. And this part, we're just looking at the pellet acting on the rocket. And that's what force is. It's the thing that moves aircrafts through the air, using Newton's third law, basically, to make that something that works to propel it. So we're actually given the values for this, and we also solved for the equation in the previous step. It's going to be that same change m over change t times v exhaust. So we only have to convert that 4.0 kilometers per second to meters per second. Once we do that, we can just plug in those numbers, and it comes out as being 20,000 newtons for the thrust on that rocket. So that's the answer to part B. Thank you for listening.